12.4. I'm not going to do 12.5 at all. If you're interested in it, there's a video in the old video file. May or may not let you in, but I'll fix it so it can let you in if you want to see it. It's all about finding, for instance, if you know the density of something, but it's not obviously a homogeneous density. So that is, it goes from one end to the other. It's more dense on one end than the other. You're like, where's that going to happen? Well, charge density is a place where that shows up frequently. Also, can be thought of too. That's the biggest place you guys will see. It's talking about more like a charge density situation. But so if you know the density of how it is on there, then you can find the total volume of the thing, total mass of it, whatever. You can also find the center of mass of it, all that good stuff. It's nice, but once you've seen how to do double integrals, it's really just a matter of following the formula. So it's not like it's a big deal. Some years I do it, some years I don't. I don't know. I feel like we're not really, I feel like we're not pushed, but if I get rid of one, I feel like it's just about the right amount enough to finish it up. So 12.3 and 12.4 tonight. 12.6 is the video this week, which is surface area. I do that as a video always because it's a situation where I want you to see that, I do it pretty much entirely in Excel because surface area is always a double integral with a giant square root. And inside that square, you've got functions that are squared. And they just never, yeah, go ahead, put it down, never work out nicely. Okay? Unless it's a plane. Jay, if it's a plane, it's a freaking rectangle or something, so why are you using calculus? I'm just going to ask you guys. Okay? So, whatever. So there's that. But so I do it in there so you can follow along on Excel, see which buttons I push, make sure you get it all typed in right, run it back 7, 8 times. Go, oh, yeah. 12.7 and 8 in class next week. No, 12.7 and 12.9 in class next week. In my mind, Stewart has it backwards. 9 is the generic version of how to do it. 8 is a specific version of one thing. I don't know, call me weird, but I've always been more in line with this is how you do it in general. Oh, and here's a specific case of it. So that's what 12.8 will be about. I vaguely remember that, and I vaguely remember a lot of memorization in this class when I was in college, and not a lot of where did it come from. But if you understand what 12.9 is, then 12.8, you could theoretically, if you're on a deserted island, cook up what happens in 12.8 using what you know from 12.9. But again, get a hammock, catch some fish, catch some naps, work on your base tan. Okay? That's the order of things to do on a deserted island. Okay? In my opinion. All right. Now, tonight, as I say, we're going to be double integrating, and we're going to be doing that over a region. But a region that is not defined by a rectangle anymore. So I'm pretty much going to do this one pretty much all night. X plus y. Why? Because it's easy. Okay?
Did you start recording her?
I did. I did that way because I don't want to spend hours tonight going, oh my God, I got to do another integration problem. Okay? Obviously, when you go home, break out the 89s, do it on 89, that's great. What I kind of want you to see is it's the same integral every time. All I'm going to change is what we're integrating it over, what region. Okay? So last week we did it something like this. So I don't know, we went from like 3 to 6 and I don't know, 1 to 5. And so again, what does that look like? Well, y's come first. So 1, 2, 3, 4, 5, 6. And 1 and 2, 3, 4, 5. So we're integrating it over this region, right? That rectangle. This will be the only one tonight we do it that way. In a minute we're going to change it up. I will continue to draw these either by hand or I will bring up a graphing calculator and graph those regions so I can see what I'm integrating it over. I don't expect you to be obviously a rectangle. I hope you can do them. Okay. But as soon as we move away from a rectangle, they get a little ugly. And the fact that they get a little ugly, that means I want to see what the graph looks like. Okay? And not necessarily a sketch like this, maybe one that's a little prettier. So I will usually use Desmos because I think it's quicker, but use your calculator. Use a way to see what this region looks like that we're integrating it over.
Which one's, what's the order again? X?
Oh, yeah, so right now, the way I have it, we're going to integrate over the y's first because it's on the inside, okay, and then over the x's. Yeah. I could just easily flip-flop these two easily and flip-flop those because it's just a rectangle. But in a minute, I can still flip-flop them, but it's not going to be as easy anymore. So let's review here real quick. So last time we met about this stuff, we did the antiderivative, which of course with respect to y is going to be xy plus y squared over 2, right? From 3 to 6. Oops, what are you doing, stupid? Dx, there you go, 1 to 5. Now, if you plug in a y equals 6, you're going to get 6x plus 18 minus 3x, and then plus 9 halves, I guess. Is that right? I think so. Good. And if you clean up your like terms here, you're going to end up with 3x, like plus 13 and a half, or thereabouts. Yes? 27 halves, if that makes you happier. Again, still haven't integrated with respect to x yet. But that's just our intermediate step. This intermediate step will be different in a few minutes, of course, when we change these bounds of integration here. So this intermediate step will be different, but this first antiderivative, of course, will be the same, yes? So pieces and parts of this will be the same, but obviously this bit here will be different because we're not going to go from 3 to 6 in a minute. We're going to do something different, okay? If you integrate this guy, what are you going to get? 3x squared over 2 plus 13 and a half x from 1 to 5. So we got 75 halves. Oops, there's an x there, dummy. There you go. I can't do that in my head. Let's see, 65. That's not right. Yeah, 67 and a half. It is 67 and a half, isn't it? Yes, it is. Good for me. Good. Maybe. Come back here. Plus 67 and a half, I think. You should probably check me, but I feel pretty good about that. Minus 3 halves. My plus, yeah, so it's 13 and a half. There we go. So, what do we get here? So here we've got 1 and a half plus this is 15. Okay, and this is like 37 and a half. So is that 105, I think? Is that right?
When did you
I think something like
replace
that.
the Y?
Hmm?
When did you replace the Y?
That was like literally step 1.
Oh,
Yeah, step 1. We integrate with respect to y, substitute them in. Okay? Again, don't worry about the calculator. I mean, yes, I don't care if you use the calculator. I still want you to do a few of these by hand. Again, we're only going to integrate nice, easy ones this evening. Okay, so the antiderivatives will just be easy money. Boom, 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 boom. Almost everything we're going to focus on tonight is the limits of integration, the bounds. That's what we're going to spend all of our time on tonight. This is obviously supposed to be a refresher course, this piece here. So hopefully we feel good. Is it 90 to check me?
Yep.
Nice. All right. So you're like, well, let's do another one, but let's change it up. Okay, cool. So let's go x plus y dy dx from 0 to 2 minus x. Ooh, nice. And let's go from 0 to 2. I think I might need a graph. I think I might need a picture. Now, this one is pretty easy to sketch because I've been teaching math for quite some time now. But if you've not been teaching math for a while and you're like, I can't really, I don't trust myself, well then for God's sakes, get a calculator and graph it, okay? I don't work for this company, although I think I'd like to work for them. I read about them one time. You need a PhD. But if you did work for them, they never want you to work tired. So literally whenever you show up is fine. Yeah. Catered lunches every day. Yeah. Recreation through the day. It's one of those touchy-feely companies. Ah, sounds good. Pays good. Just don't have a master's degree. Or a PhD, I mean. So 2 minus x, there's that function, yes? I'm going to also graph y equals 0. Oops, no, not on the same line, though. Not on the same line. There you go. Y equals 0. Now, why did I do that? Because, back in our notes, you'll notice that the y's are bounded by y equals 0 and y equals 2 minus x, yes? Right? So where on the picture are we? We are right. We are in between this blue line. Oops, I forgot to put it in projector mode. Sorry about that. We are between this blue line and this red line. But where? I don't know. We need to pinch the x's somewhere, yes? Well, the x's are pinched between x equals what? 0 and x equals 2. which is nice. So you can literally type it in over here somewhere. Come on, give it to me. Give it to me. You can type in x equals 0, and you can type in x equals 2. Okay? And so we're looking at this triangular shaped region in here is what we're looking at. Okay? So instead of integrating over a rectangle this time, we're integrating over this region in here. Again, this one's pretty easy because it's nice and linear. Later on, when it gets a little trickier, a little messier, I highly recommend you use a calculator. Okay? Because you think, oh, that looks right, and it's not right, if you're like me. Okay? So to me, that's the way to go. I'm going to copy this and paste that into my notes real quick so that we can take a peek at it a little closer. No thanks, I don't want to rate it. There we go. Nice. Cool. And copy, and close, and open. I hate when it does that. And so here's my picture. And again, we are integrating from 0 to 2 minus x, and from 0 to 2. So that's this region in here. X plus y, dy, dx. Okay, that's what we're doing. Now, it's important to note that we are integrating with respect to y first, yes? Okay? Meaning that the only variable that can possibly be on this guy here at all is x, yes? Because I'm getting rid of all my y's on this step, and I'm replacing them with x's. That's a huge concept. You cannot have any x's out here. I don't want any numbers left when I'm finished. Right? I don't want any letters floating around when I'm done. These better be all constants out here. If they're not, you don't try it. Stop. Go fix it. But again, I'm integrating with respect to y's. Only can be x's up here. If you have y's up here and here, that's a bit of a problem. It's a big problem, so fix that. So we're going to look at this in a few minutes, how we can flip-flop these around, and we can. But for right now, it's important. If you're going to integrate with respect to y, your bounds better have x's on them. If you're going to integrate with respect to x first, then your bounds better have y's on them. Okay, so that they cancel out properly. All right, so I already did this last time. It was x squared over 2 plus xy. Oops, I'm sorry, I did it backwards. That's y squared over 2. Thank you. Let's try it again. Let's write it backwards. Alrighty, let's try it again. So it's xy plus y squared over 2, right? But this time we're going from 0 to 2 minus x. Yep. Wow, that's going to be fun. So when you plug that in, what you're going to end up with is, you're going to end up with x times y plus y squared over 2. And then when you plug 0 in for the y's, they both go away, yes? So that's kind of handy. That makes it nice. And then, yeah. So so far I've integrated this way. But now I'm going to integrate. Where did I go? I'm sorry. Where did I? Yeah, that's right. I've integrated this way. Now I'm going to come across this direction. Okay? I was like, where'd my y-axis go? But I forgot my y-axis is over the green line. Okay? All right. Now this is where it's a little messy, and a guy might want to clean this up a little bit first, right? I mean, yeah, you can do substitution. I don't want to. I got better things to do. So I'm going to probably FOIL that out if I'm doing this by hand. If I'm not doing it by hand, I just type it in my calculator and do it all in one fell swoop. So this is 2x minus x squared, and this is x squared minus 4x plus 4 all over 2. Oh, yeah. So if you clean this up, this is a negative 2x, that's a positive 2x, they go away. Here's a half an x, here's a negative x, so that's a negative x squared over 2 that I'm left with there. And this is just plus 2, right? Yeah, so plus 2. Again, that should be what it cleans up to if I didn't screw it up. And then integrating it is simply negative, what, x cubed over 6 plus 2x, from 0 to 2. So that would give me negative 8/6 plus 4 minus 0, which is, what, 2 2/3, I think? or thereabouts? Nice. Can we check that? Do you mind?
Yeah, it's 8/3.
8/3.
Sounds about right.
There it is. Nice. The crowd goes wild. Okay? Now, as far as typing this into my calculator, is it any harder than we did before? No. No. It would be integrate, or well, I'm sorry, I started to write it. Integrate, obviously. Yes, you're going to have to do these by hand on the test. That's why I'm, going through this right now. So just be aware of that. Parentheses, comma, x, comma, 0, comma, 2. Just like that, should get the job done just hunky-dory. The only difference is we didn't go 3 to 5 and 1 to 6 or something. We're actually putting the functions in there. Everything goes in the same place as before. We're just changing it up with some of these functions. Questions on that part? Not too bad, huh? It's not horrible. Could be worse. Okay. Question. A minute ago, it was the area, the volume was how much? Was it 90 in the last problem?
Yeah.
Why is it so much smaller this time? Smaller region, that's one thing. What else? Last time we were on this plane, x plus y, we were out further, yes? And the further out we get from the origin, what do we get? We get a bigger z value, yes? So we're getting quite a bit more volume under it, because we were out here, go over from like 1 to 5 and 6 to 8 or whatever it was a minute ago. In here, we're pretty tight to the origin, so we have pretty small volumes, yes? Always positive, because the way I happened to done this problem, it was all in the first quadrant, and x plus y in the first quadrant is always positive, so awesome. Yeah? Yeah, not too horrible.
Good. Good. Sorry.
Okay, freaked me out, man.
Just got to work on my calculator. Like, oh, great.
It did work? It didn't work.
It did.
Nice. All right.
6.66666.
Nice. Check it out. X plus y. Ooh, dA. Remember, dA is the generic over some areas, right? The little areas, dx and dy's and dy dx's. Okay. But let's bound it differently this time. Let's say that y, let's write it this way and see what you think of this. No, sorry. Yes, x, and 2, yes, yes, that'll work nicely. Good, that. So I want to pinch my y between x and 2 minus x. Why? Because I feel like it. Okay? I'm the boss. Dadgummit. All right? I feel like my boss literally today because I'm the boss. So whatever. All right. And yeah, I don't know. I guess we could do another boring one like this: 0, x, 1. Okay. So if you were to look at the graph of this guy, again, if you've taught algebra for a while, you know what this picture looks like. But if you don't, this is what graphs calculators are made for. So use them. So 2 minus x, we still got 2 minus x. But you could do just y equals x right here. Oh, nice. And then you could do x equals 0. And you could do x equals 1. Oh. And so it's this region in here is what we're integrating over. This triangular shaped region in here. Okay? Let me blow that up a little bigger so you can see it better. Yeah, this one. Nice. Now, when we do this, again, I'll copy that so we can see it more better. And you're not pasting. Why aren't you pasting? It hates me, that's why. I don't know, whatever. So it looks something like this. That's the region we're integrating over. Okay? Now, as we're doing these problems, when we're integrating, let's think about what we're doing here. We're saying the y's, we're going from a low or a floor of this guy, yes? It's bounded below by this one up to a top of this one, yes? And the x's minimum is 0, maximum is out here at 1. In a minute, we're going to switch this around and do it the other way around. This is the most convenient way to do this problem because I can do it all in one fell swoop. I can do it just in one pass from here to here because there's one bottom function and one upper function. So it's bounded easily this way. and it's bounded easily this direction. In a minute, I'm going to do it the other way around, which is possible, it's just grosser. I'm going to have to do it in two pieces, and that's fine. Why would I do that? I show you this because sometimes you might come across one where the book suggests that you do it one way, and you're like, that's two pieces. If I'm smart, I can do it in one piece. And so it's easy to be able to flip it around. Again, it's possible to integrate in both directions as long as you're, careful and don't screw it up. All right, so let's try this. From x to 2 minus x, x plus y. 0 to 1. All right, so xy plus y squared over 2x. Bless you. Bless you. Something along those lines, yes? Oops. From x, what are you doing? Yeah, from x to, there, xy plus y squared. There, that's what I wanted. From x to 2 minus x. There you go. 0 to 1. All right, so if you plug in your x, your y, so it's x times y plus y squared over 2 minus x times y, so x squared, right? Plus x squared over 2, right? And oops, whenever we get done with that, we're going to have a dx, and we're going to go from 0 to 1. Why is it a y? That's a good question. At this juncture, there should be no y's left. You see that? If there's any y's left, you have issues. You better fix that. Okay? All right, let's see if we can fix this. So it's 2x minus x squared. And then when we get here, we get 4, so half of 4 is 2, and you get 4x, so negative 2x, and x squared over 2 is positive, and a minus x squared, and a minus x squared over 2. So these cancel, and that becomes negative 2x squared, and those guys cancel, and plus 2, right? Yay. Aren't we all glad we have calculators now? I sure am. But it's nice to know that you could still do it if you had to. So, it's negative 8/3 plus 2 should be negative 2/3, I think, right? Should be negative 2/3. Negative 2/3. Am I shocked by that? I don't know. Am I shocked by that? Should I be shocked by that? Does that bother me? Should it bother me? Feels like it should bother me a little bit. You should check my math on this one. I'm not feeling
It
confident.
says 4/3 on that.
Good, because I had problems somewhere. Again, why did I know this going into this? Well, I know what x plus y looks like. I know that in the first quadrant, it's always positive, yes? Could I end up with a negative volume? No. So when I get down here, I'm troubled slightly by this. That doesn't look right. I know it's x plus y is positive in the first quadrant, but if I didn't know it, if I didn't know what my shape looked like, shame on me, because I should be using my 3D calc plotter, and I should be looking at it and going, look, the predominance of my structure is positive in this region. Hence, my volume had better be positive. If it's about half and half, and you're like, well, I can't really tell, and I get 2/3 negative, I'm like, I'd probably buy that for a nickel. If it's mostly negative and a little positive, I get a positive, So kind of get those thought processes going in my mind. So again, x plus y in the first quadrant, all positive. The fact that I'm getting a negative here is bothering me a lot. Okay? It should bother you at some point, hopefully. So what'd you say it was?
4/3.
So he's telling me it's 4/3. So suffice it to say, somewhere in there I made a boo-boo. Okay? Not necessarily want to chase it down right now.
Right at the
Okay.
end.
What's that?
Right at the end.
Where was it? What did I do wrong?
You did 1 cubed is 8.
Ha! 1 cubed is 8. What a moron. Oh, 1 cubed. Ah, there you go.
Did the 2.
There you go. Yeah, there you go.
I did not know that.
Negative 2/3.
Thank you. But still, yeah, there you go. So, yeah, 6, yeah, Ta-da! Nice. Again, glad I have a calculator.
What's the
But
original?
more importantly, I am glad that I have a grapher. Because I'm glad that I can look at a problem ahead of time and go, this better be positive. Or my answer should be a huge positive or a big negative, or it should be close to zero-ish, or it should be, or whatever. So that when I do the problem, I'm like, oh, that looks weird. Or, yeah, that's about what I expected to happen. Okay? So we'll do some more later on that are maybe a little more different. But for the first ones, I want to just kind of stay with this just nice, easy problem. Don't get too weird. Don't get too crazy. Okay? What were you saying?
What was the original function?
X plus Y again.
Oh, just x plus y.
Yeah, X plus Y. Why? Because see, it's just easier to stay with the same function every time. I don't have to worry about this whole business. And I really want to focus on the doing tonight, not the typing in, being button pushing monkeys, okay? Because we'll get to that in a minute, but not just this instant. Now, let's change this around and let's do dx dy this time.
Is it X plus Y still, or?
Oh, I'm sorry, yes, thank you. X plus Y. Thank you. Same function. But here's the deal. Nice. Well, if I'm doing dx first, x needs to be bounded by one function on the left and one function on the right, yes? Well, this function right here happens to be x equals y. Not y equals x, it's x equals y, right? That's his other name. The other one is, of course, this was y equals x, or 2 minus x. But another way of writing that would be, of course, to write it as x equals 2 minus y, yes? Like that. So I can write this as 2 minus y. So if you look at it, x is not bounded on the one side by one function. I mean, it is on the left side. But on the right side, it's bounded by this one part of the time. And it's bounded by this one part of the time. Which means I'm going to have to do a sum. So I'll write it down here so you can see this better. I'll write it this dx dy, x plus y, plus x plus y dx dy. So let's do this bottom half first. Right here is where it splits, yes? Right here is where it ceases, because from here to here is bounded on the left by one function and on the right by one function, yes? So it's bounded on the left by 0, x equals 0, and it's bounded on the left by x equals y. Again, be very careful. We're integrating with respect to x. Better be y's up here. Okay? Okay. And on the other one, of course, we're going to go from 0 to 2 minus y. Right? And then lastly, we're going to do our y values, yes? So for this bottom part, our smallest y we can ever have is, right down here, 0. And our biggest y we can have in this region is 1. And for this region, our smallest y is 1. And our biggest y is 2. Same region, better be the same volume. Huh? Better be the same volume. So it better still be 4/3 again, yes? Now, David, I know it's not that I hate you, that why I'm doing it this way, okay? Okay, because some people are looking at me like, why are you doing it in 2 pieces? I don't want to, but I want to show you the same thing, okay? And sometimes you're going to get a problem that's going to be written with this bounds over here, and you're like, should I do dx, dy, or should I do dy, dx? Well, whichever is the easier way, which would be to do it in one piece, if possible.
But I thought
Okay.
that it mattered which order things were going in.
You can do them.
Oh, is it just that as long as the thingies match up, they're sandwiched correctly, like
Yeah.
Okay.
Literally, that's what I'm
You couldn't
saying.
just you couldn't flip the dx and the dy without flipping the integral signs.
Well, it's more important than that. I flipped the integral signs, but I also changed what these bounds are. They're not the same as they were before. On the very first problem, since it was over a rectangle on the very first problem, yeah, you can just play musical chairs with these guys. But I actually have to change things around because I'm bounded by a function now, by functions now. Wake up. God dang you. Because I'm bounded by functions now, and so I can't just do it with, I can't change it around on a rectangle. So, here's this deal. Yeah. So again, it's just what? It's x squared over 2 plus xy this time. 0 to y, dy. 0 to 1. So if you plug into y's, you're going to get y squared over 2 plus y squared, right? Okay, which is handy because that's just 3/2 y squared dy from 0 to 1. Well, if you antiderivative that, you're going to get, well, you're going to get 1/2, aren't you, I think? Y cubed from 0 to 1, which should give you 1/2, if I'm not mistaken. That's for the first portion. Okay, so that's the volume on this first portion. There's some volume over that first bottom triangle. And then I do the second part. I have a hard time doing one thing at a time, much less two. So we'll just do them one at a time. So x squared over 2 plus xy from 0 to 2 minus y dy. Now we're just going to substitute that in. So you're going to get 2 minus y, 2 minus y squared over 2 plus 2 minus y times y. Right? Right. From 0, oops, what are you doing? dy 1 to 2. So if you clean this up a little bit, come on, stop it. So it's going to be negative y squared over 2 plus 2 minus 2y. And over here you're going to get a plus 2y and a minus y squared. So those cancel out. This should be a plus y squared. Right. So it should be negative y squared over 2 plus 2 dy from 1 to 2. And so this would be like negative y cubed over 6 plus 2y from 1 to 2. I really hope this works out. It's looking good because I got a 6 down here, so that makes me pretty happy. It's going to be negative 8/6 plus 4 minus negative 1/6 plus 2. And so it'd be positive 1/6 minus 2. 8/6. So, I messed up somewhere. All right. Yeah, it should be a plus 4. Thank you. Phew. Phew. So there's 2, and then it's minus 5/6, right? Which is 1 and
Minus 7, 6.
what's that?
Minus 7.
Thank you, minus 7/6. I'm going to use my calculator from now on because I'm getting really tired of making dumb mistakes, okay? So 5/6 plus 1/2 is what? 8. So I still made a boo-boo somewhere. Oh, was it 4/3? I was thinking it was there. Good. 8/6 4/3. Well, how about that? Yay! I did get one right. Yay! Anyway, enough of this foolishness. We're going to use calculators in a second. Okay, but hang on. Hold on. So one can see where back in the day we had it hard. I don't think I need to sell that. I don't think you can oversell that. How long it took to do this little farting around here? Oh my God, it's horrible. It's horrible. All right? But again, the idea is it's not that hard to do them by hand. It's just there's so many stupid little mistakes, getting lost along the way. And again, the one we did prior to this, I could do it all in one integral. Way nicer. Doing it this way, 2 integrals, not so nice. Doable, not so nice. Yes?
How do I do an integral put an integral into a 3D cup of water?
You don't. You don't. No. If you're going to do, you don't. That's what I just said. You don't. You're either going to use Maxima. You're going to use a TI-89. You're going to use Wolfram. I'm sure there's some other calculator thing out there you could find. Knock yourself out. Don't care. Okay? Because you just need to know how to pull them off. Ooh, here's a fun one. Well, actually, I'll just graph it on I'll do it on the computer so it's prettier. It's the 21st century after all. So, 9 minus x squared. And home. Oh, there, that's pretty. Nice. And, x plus 1. Oh, that's nice. Nice. Good. So I would like this region in here. This region up in here, that's the region I want to integrate it over. Maybe. If I can. What are you doing? There we go. This region up in here is the region I'd like to integrate it over. And so I'm going to do. That's what OneNote's for, Jay. Just copy it. There you go. Cut. So let's think about this. Come on, give it to me. Where's the paste button? For God's sakes. There. Ta-da! Alright. So it's this region in here that I'd like to integrate over. I don't care what the function is right now, but that's the function I want to integrate it over. Okay? That's the region. Okay? Would it be better to do dy dx, that is you go from bottom to top, and then from left to right? Would it be better to do it that way, or would it be better to go from left to right and then up and down? Do you think? And when you're answering the question, ask yourself this. Is it bounded below by one function and above by one function? If it is, then it's best to do dy dx. If you're going to see multiple functions over that region, that's not a good idea. Then ask yourself, is it bounded on the left and the right by one function over here and one function over here? If it is, that's a better way to go. Okay? So which is it?
dy dx.
It's much better to go dy dx because there's one bounded function on the bottom and one bounded function on the top. Yes? So if we were doing this, we'd be going from, this is what it says, x plus 1 or something, I think. That's my lower function. To 9 minus x squared on the top. Again, dy. And then dx. And where are my x's going from? I don't think I copied the numbers. But one could see, and all the ones that Stuart gives you will be pretty, they'll be like easy numbers like 2 to 6, Jay, isn't that great? But here, negative 3.3, positive 2.3. Okay, and as many decimals as you like. Okay? Pretty much just want to think about how I set this problem up right now. So negative 3.3 and positive 2.3. If you like the 7, you can have the 7s too. Okay? And that's the game. Once you get that figured out, boom, away we go. We're off to the races. Okay? Doesn't matter what function you put in here particularly. Any function of x and y would probably be better, Jay. That a kid. Doesn't really matter what function you stick in there. You can do x plus y, pretty much any function as long as it exists over that region, yes? Okay. So again, I'm just going to use x plus y. I'm going to break out my calculator. I'll do it in Maxima here in a minute too. For those of you that need to do some other version, we can do it that way too. I think. Come on, Betsy, wake up. There we go. That's your 83, stupid. How about you use your 89? There you go. Ta-da! All right. Home. So integrate. Integrate. So just x plus y, comma, y, comma, x plus 1, comma, 9 minus x squared, parentheses, comma, y, comma, no, not y, comma, x, comma, negative 3.37, comma, 2.37, parentheses. 104-ish? 104-ish? Ta-da! There you go. Nice. Questions? Questions on the gist of it? You're going to do more. Yes?
Where's
So, but here's the deal. So you do it over the line y, so you're putting in a y squared, right? So then when you evaluate the negative 3.37, what are you going to do to it? You're going to end up squaring the thing, aren't you? Where you're going to end up, when you plug it in, if you do that math slow, we can actually run it through for you. But if you think about it, okay, so remember it's x plus y, so it's going to be xy plus y squared over 2, right? Okay, and then you're going to be plugging in the functions. What do we do? X plus 1 on the bottom, and what was it on top? 9 minus x squared on the top, right? So if you plug those in, you're going to get 9 minus x squared times x, right? Plus 9 minus x squared over 2. All right, minus, and then you're going to get x plus 1 plus x plus 1 squared over 2. You do the math on that, and then you integrate again. You can see where you're going to be getting a cubic. Well, this is already a 4th power right there. You see that? And you integrate again, you're going to get a 5th power coming out of that mess, right? After you FOIL that mess out and do it. So you can see where we're going to get a fairly large number fairly quickly out of this mess. That's where it's coming from. Okay. A lot of that does get lost in the translation, right? Because you're not thinking that in that regard. You're not really thinking like that because you're like, oh, it's just small numbers. Yeah, but over the region, because we're going up there, up to 9. Okay, we're going to see some of that a little bit better.
And then on top of that, it's a larger surface area, so as it's ramping up for volume, you're also covering the bigger area.
Well, but on the plane down here, this is staying constant down here. We don't really worry about the surface area of the slanty piece.
No, it's
Okay.
the volume underneath it.
No, for sure. The further out you go, yeah, sure. And again, all the way up, all the way straight up through here, all the way straight up through here, right? This is all positive over in here, obviously, right? Okay. Over in here, our y's are quite a bit bigger than our negatives, right? Or than our x's. So x plus y, well, they're still going to be positive, aren't they? Okay. The only place we might see some we'll obviously see negatives down in this region, obviously, but not too much. And we'll see a few down into here because where? Right along this line, y equals negative x, it's going to be 0, yes? So pretty much from here down, these are going to be negatives, but all this crap up in here is positive. That's why it's going to be coming out that way. Okay? But again, when in doubt, go to your 3D calc plotter and take a look at it. By the way, I ordered a pair of 3D glasses. They finally showed up the other day. They're at like $2 special off of Amazon. I ordered them a long time. They finally showed up. I was like, oh, I forgot I ordered them. I was a little bummed out. I thought the 3D would like pop a little more. It doesn't. It's nice, but it just, I don't know. I put my Chinese lead-infused glasses on my face, and I'm like, maybe it is popping, man. I don't know. Anyway, it's a little weird. Now, check it out. This function over here could also be thought of as what? Because right now it's y equals 9 minus x squared. But how else could it be written? Yeah. So let's play some musical chairs. So x squared is equal to 9 minus y. And then, of course, x is equal to, wait for it, plus or minus 9 minus, or square root of 9 minus y. Interesting. The plot thickens. Now, here we go. This is negative square root of 9 minus y. And this is positive square root of 9 minus y. And this function here, which of course was y equals x minus 1, or x plus 1, right? Is now going to become x equals y minus 1. Right?
What's the purpose of
Okay.
switching the variables again?
Knowing, because I'm going to integrate the other direction this time.
Okay.
Now, this time I want to go from where to where? I'd like to do dx dy this time. Just to see if, again, to know that I can do it if I need to. Okay? Well, if I start on this side, that's obviously my left-hand endpoint, obviously, yes? And I come across, and is it bounded on this side by a function? Well, yes, it's bounded here by a function, right? Up until I get to O right here, yes? In other words, if you split it straight across, right there, the lower half is bounded on this side by negative 9, oops, wrong one, dummy. Negative square root of 9 minus y on the one side, and y minus 1 on the other side. Right here and right here. Okay? And my y's are bounded by whatever that value is, I'll have to go look it up, are bounded by negative 2.32? Well, duh. Negative 2.32 and positive 3.37. Yeah, there it is. So negative 2.3 and positive 3.3. No, what? What? Yes, 3.7. Yes, 3.3. 3.37, 2.37. Okay, so that takes care of this lower end. Now, what would the upper part look like? Well, again, it's bounded on this side by this guy. Okay, that can just go away anytime. Stop it. There. But this time it's bounded by this guy on the other side, yes? So square root of 9 minus y. And my lower bound then is this guy right here, which is 3.37, right? That's my lower y value that time. And my upper y value is this guy, which is y equals 9. And you pick it right off the graph. Okay, you can pick it off the graph. You could also go, if I have 9 minus x squared, when x is 0, you get y is 9, right? Okay. And again, why do we do it both ways? Because sometimes it's helpful to do it both ways. And I really want you to be confident to be able to do it both ways based on what the problem suggests. By the way, I will give you extra credit on your box project. If you're doing the box project, I will give you extra credit if you make yourself an oddball shaped box. For instance, I will give you way more extra credit if you do a circular box, because that's really gross.
How is it, if it's circular, I don't, is it?
Like a hat box. Like a hat box. You could also build yourself a triangular shaped box, not unlike this one. The tricky part is then squishing your function so that it has max, minimums, and saddle points in there. But if you do it, I'd give you a little extra credit because it's a little trickier. A couple years ago, don't do this by the way, a couple years ago this guy went out to Michael's and he bought a Christmas tree ornament that you can make your own Christmas tree ornament, but like you take it apart like this, and he built his model inside of a sphere and integrated with spherical components. You talk about a god-awful mess, friends. Wow, that was a mess. Oh, man, I don't want to work that hard to grade your problems, to be quite honest with you. That was a lot of screwing around.
Is it,
Points in this that much of a pain to grade it.
I still have that one. I still have about 7 or 8 over the years that have been really, really good / cool / I can't really throw that away. I've kept them. Others I have pictures of, but wow. Wow. Anyway, I saw it. It looks neat in a little thing hanging there or whatever, but wow, it was hard. Yeah.
so did you, back then, was there Wolfram Alpha or?
Okay, this was not a million years ago. It was like 2 years ago. It was,
Oh,
like,
2
it was
years
literally
ago.
2 years ago. Yeah. And I will say this, that he used Excel to do the double integrals, like a normal human in that situation, because it was just gross. Okay?
Excel could do that. I would think Wolfram or.
Well, no, because it punted. Okay? If it's too messy, if Wolfram will tell you, they say something like, please buy our package, which is basically, screw you, we're not doing this for free. Okay? Maxima will probably do it, although it may give you an answer that you don't like. Sometimes it gets messy and it doesn't want to do it, which is fine too. Your calculator probably won't do it if it gets really messy. So, just go to Excel.
I know sometimes it does. It's just that you need to, in order to
Right.
see the full function, you need to like hold down the arrow
You get it?
key for 5 minutes. Just to,
No? Didn't work?
What were the?
Oh, I'm sorry. You're still working on it. I'm sorry. I'll shut up. I'm sorry. All right. All right, I'm about done with x plus y. I'm going to try a different problem here in a minute. Kind of bored of this one.
I'll take a picture of it so you can put it on.
Are you sure? Okay. All right. Nice. All right. So now you're thinking, well, this is weird. I think it'd be really cool if we could do one that looked a little different. I think so too. Nice. So what if I did x equals 4 minus y squared? By the way, that's the other thing I love about Desmos. Doesn't care if it's in x equals, if it's in y equals. Just graph it. Happy as a clam to graph. Glad to help, Jay. Whatever I can do. Nice. But wait for it, I'm not done yet. I am literally not done yet. Mm-hmm, mm-hmm. Mm-hmm, 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 mm-hmm. God
So I got the same answer.
damn. Yay, you got the same answer. Nice. And we're not copying. There you go. Nice. You're like, what area are you gonna integrate over? I haven't decided yet. I'll tell you in a minute. I'm just making this up as I go. Whatever. The other thing I like about x plus y is it exists everywhere. So wherever I feel like integrating it, I have to think about it too much. Okay. Sometimes you get a function that's kind of like, oh, I'll do this cool function, and then you're right. Ah, crap! I just integrated over an asymptote or something ridiculous. Okay. Here I don't have to think too hard. Yeah, I kind of like to integrate it over this region down in this mess. Yeah. Yeah. Now, let's think about this for a moment, shall we? Yeah. So, one bound underneath of it? Sure. One bound over the top of that region? Mm-mm. We got one bound here on the orange one, yes, and we got one bound on this black one here. So if I'm going to do it dy dx, it's going to be in two pieces, yes? So let's try it the other way. Is it bounded by one on one side and one on the other side? Yes on this side, a big fat no on this side. So then it really comes down to picking your poison. Should I do it dy dx or should I do it dx dy? And you're like, well, which would you do, Jay? Well, here's what I would suggest. I'm going to do whichever one is the easier to use, to be honest with you. Okay, so for instance, this is 4 minus y squared, I believe. Okay, equals x. Do I really want to turn that inside out and solve for y? You know, I don't, because I really don't like square root functions necessarily. I'm kind of square rootist or something. I don't like them. If possible, I like to avoid that. I'm not saying I'm not going to. I'm just saying I don't necessarily want to. I see this as y equals x cubed up here. Clearly, I've got x cubes and I've got y squareds. One of these has to move. Yes? I'm going to have to make them all x equals or all y equals. Okay? And then the other one, of course, any idiot can solve a linear function, right? Y equals 2 minus x. I mean, I'm telling you, you probably oughtn't to be in here if you can't pull that one out, right? That one's easy to solve either direction. Okay? So then the question is, which is easier to solve? Is it easier to solve for x equals the cube root of y, which, by the way, not terribly hard to do? Or is it easier to solve for, y is equal to, let's see here. I'm going to play musical chairs. So 4 minus x, the square root of 4 minus x. Oh, by the way, that's the negative half of that. I don't want to mess with that, to be honest with you. So I think I leave this one alone. I think I leave this one alone. I think I don't screw with this one. And the fact that I'm going to leave it as a function of x means that I'm going to do dy first and then dx. I'm sorry, I'm going to leave it as x equals a function of y like this. I'm going to end up doing dx first and then dy if I do it that way. Okay, dx first, then dy. Again, up to you. It's up to you. So I think what I'm going to do then is I'm going to turn this inside out and write this as x equals the cube root of y, or y to the 1/3 power. Okay? I think that's how I'm going to do it. Okay? Now, sometimes you may come across a function that's like x squared plus 6x plus 5 equals y. Good luck solving that for x, right? Because it's not an easy one like this guy here. If that happens, don't screw with it. Just integrate it the other way. Don't do algebra. Don't do any more algebra than you have to. Okay? It's just absolutely ridiculous. This one here, it's 6 of one, a half a dozen the other, whichever makes you happier. Just knock yourself out. Okay? I think I like this better because, it just gives me one extra thing to screw up. It's really hard to screw up the cube root of y. This is one extra thing to mess up here. But you do what you want to do. So let's try this. So again, that means I'm going to be doing dy dx is here. And I'm going to have to do it in two pieces. Okay, so let's start off with, excuse me, let's start off with the bottom piece. All right, so we're gonna have to split it this direction, right here, yes? We're gonna split it this way, right across through into here somewhere. So that means I need to find this intersection point right here. That's going to be a big deal. Oh, what is it?
2.5 negative?
Is that what it is on the thing? Probably.
What it looks like.
I don't know. I could go look at it. I was like touching the thing going, why don't you tell me what it is? But that's because I'm not really on the computer. It's -3, it's 3, -1. Thank you. That's nicer. This is 3, -1. Okay? So I'm going to cut it across here like so. Okay? I'm sorry. I wrote it backwards. It should be dx dy. Sorry about that. I would have caught myself in about 2 seconds. There we go. Because what am I going to try to stick into here? Well, I'm going to stick in this function over here and this function over here. What is this function? Well, it's y to the 1/3 power. Well, it can't very well be a y to the 1/3 power down here and then have a dy right there. So I would have caught myself, I think, in about 2 seconds. So y to the 1/3. Don't forget the parentheses. You'll screw it up in the calculator. It seems obvious that it's that way, but just be careful of that. And then on the other side, what are we bounded by on the other side? Well, we're bounded by this purple function, yes? And this purple function is, what is it, 4 minus y squared, I think?
I thought it was just y equals, or x, or y squared equals x, or plus 4, or something.
It's right there, 4 minus y squared.
Oh.
There it is, okay? And our y's are going from here, with this y value, which is -2.3. I'm kind of beating up the -2.3s, it seems like, tonight. From -2.3 to -1. That's for the first, that's for this bottom piece. For the upper piece, we're still bounded by the orange function over here, right? So still cube root of y. Still cube root of y. And we're bounded by the black function now, so that is, that needs to be written as, I wrote it somewhere, didn't I? I didn't ever write it.
1 minus 2.
X equals 2 minus y, right? It's 2 minus y. And we need to go from -1, that's my lower value, up to a y value of right there at that intersection point, which is
But I thought we have black.
is 1. So there it is right there. What were you saying?
Oh, okay, so what was that black line, the vertical
The
black?
black?
The vertical black line with the shaded in below, what was? Oh, was that
That's a
just the?
horizontal line of -1, because that's where I split it sideways.
Okay,
Okay, that's where I split it sideways.
I'm sorry, I got my horizontals and verticals mixed up.
So I'm told it's -1.24 for the final answer. Okay, again, 2 pieces. Once you get the hang of plugging them in, it's not very hard to do. Don't do it with my hand. Okay, the only ones I give you on the test, I promise, will be straightforward, easy to do, and problems on the test. Okay, because that's not really the point. Obviously, once they get messy, the hard part is finding the bounds. The bounds are the tricky parts. Okay, because it's algebra. That's what it boils down to. And again, on this problem, I was darned if I did and darned if I didn't, because it doesn't matter which way I go, I'm going to end up with 2 pieces in this one. Before, I could always do it one way or the other way and end up with a 1 piece. That's not always true. Okay? So, very similar to like when you're like, 5th or 6th grade or 8th grade or, I don't know, 2nd grade for some of you probably, I suppose, who's smarter than me. Look at this shape, and it's like made out of 52 different pieces. You're like, where do I cut it? I don't know what to do. And I always thought those were cool, I guess, but like other kids was like, how am I supposed to? Well, I don't know. There's a triangle, huh? How about there's a square? How do you just know these? But here, what you've got is, first of all, identify your region. Once you identify your region, then ask yourself, is the bottom formed by one solid function and is the top bound by one solid function? Because if it is, that's awesome, baby. You're done. Just integrate dy first and then dx. But if it's not, If it's not, like here's one upper and here's one upper, then turn it around. Is the left bounded by one function, and is the right bounded by one function? All the way down. Don't get hung up on this, because people are tempted to think that this is not part of the bottom. But it is part of the bottom. It's not if you're going sideways, it is part of the bottom, so be careful of that. So it's bounded here by this guy, part way on this side by this one, and part way by this guy here. Okay, so make sure when you look at those pictures, you're not fooling anyone. Question, Jim? No. All right. All right. Here's one right off the books assignment. Yes, hit me.
What happens if you have to integrate over one function?
Sorry, what now?
What happens if you have to integrate a volume under that's bounded by a single function, an implicit one?
Like a, I don't
Like
know.
a circle or an ellipse or something?
No. We don't, you're not, no. You don't bound me by a circle. You bound me by a sphere? That'd be interesting. Or you mean down the XY plane? Oh! Look what he said, people. How cool is this? You mean something like this? Like that?
Yeah.
He's a little ahead of me. This one here? Nice, huh? Very nice. This is x squared plus y squared is 9. It's also y equals, what? 9 minus x squared, square rooted, plus n minus, the top and the bottom. So, excellent. That's beautiful. I understand what your question is now. I'm like, what are you doing, weirdo? I got you now. So, if you do dy first and then dx, you'd go from this guy to this guy. And then you'd go on the x from where to where? Careful.
3 to negative.
From -3 to 3. Always from left to right. It's beautiful. It's beautiful. Absolutely beautiful. Hold that thought. We're coming back to that because 12.4. Oh, circular regions, but wait. I feel like we know how to deal with polar form. Interesting. So if we look at it in a polar format, what's the radius of this circle? 3. And what angle corresponds to this whole mess? Yeah. So if you let the radius go from 0 to 3, and then wrap that baby around a whopping 0 to 2 pi, you would trace out the same region. Okay? And so this one's nice because it's nice and circular. That it lends itself well to both. There are some that are going to be like particularly curvy and goofy looking, where polar form is going to be really handy. Other times it's like, this one here is 6 and 1/2 a dozen the other. Okay? Honest to God, I don't know which one I choose on this one, to be honest with you. If it's in section 12.4, I'd probably use polar form because that's what I'm supposed to be teaching. If it's in 12.3, I'd probably do rectangular form. If it's just any given day of the week, I'd probably do rectangular because that's kind of the way my brain works. But several different tools in the shed, and the idea is, why would I want this one? And hopefully you see before we're done that there's a reason for why we have different tools. There's a lot. I was looking last night, there's a guy who's selling this toolbox that I saw there. That's a good price. It's full of a bunch of weird tools I would never use. And I'm like, well, it doesn't bother me, but then it's like, I wish that it was a little cheaper, but then you see all those tools in there, but I don't use those tools, so it's not really that good a deal to me, because I don't really use a bunch of crap I don't use. And I got to think about, there's a lot of tools in the plant that I don't use. So people do use them and they're proficient with them, but whatever. So you end up using the same stuff over and over and over again in your life because that's what you do in your job, in your house, or whatever. Yeah. So you get good at them. And so sometimes I hate the expression that, if the only tool in your box, what is it? If the only tool in your box is a hammer, every problem looks like a nail. Every other stupid administrator I've ever worked for brings that thing out. I'm like, bury it already. All right, yes, we've heard your stupid little analogy thing. Okay, I get it. Get a better tool. Yeah, okay, great. Whatever. It just drives me a little bonkers. But we do tend to think that way because our minds tend to think a certain way always, and sometimes you get yourself into a rut because it has to be done this way. It doesn't really have to. Okay. But there. Others of you might look at this problem, see it completely backwards, and think of it as this guy. What? Nice. And so you broke it into the two side pieces instead, yes? So if you did that, it would be from here to here, and it would be and then from -3 to 3 on the y-axis, yes? This is dx, dy. By the way, people are tempted to always go, oh, yeah, the answer is 9 pi. No, it's not. No, it's not. You're trying to find volume, right? You're finding the volume up and over the top of this circular region, yes? So it's kind of a tricky deal. This is why I say if you're doing this volume over the circular region, that's why we give you a little extra credit for this guy. Because most of us, think about the function that you picked for your project, most of you. You picked something like cosine of x plus sine of y or something or whatever, something along these lines, or maybe you've got an e to the whatever and all kinds of grossness, right? Now integrate that over the square root of x squared. No, it's not fun. So that's why I give you a little extra credit if you want to do it that way. Okay? Got it? Is that good? They're working?
Yeah.
Nice.
My calculator's like 10 times smarter than me, so you gotta figure out what it's doing before.
Oh, you got an instinct. Yeah, those goofy things. Good Lord, I hate them. All right. Yeah, so, and here's a situation where this one's kind of gross. I won't try this one by hand necessarily. I will just do the first step kind of by hand. But if I'm doing dy dx, it's xy plus y squared over 2. Then I'm going to end up, this one actually isn't as bad as I was thinking it was. Okay? But to do this, this is going to be 9 minus x squared over 2. That's the only part I really wanted to go to at that point. This is one that Stuart would do for you, because back in the day we'd have to go, oh look, substitution, how fun! There's my u, and there's part of my du right there. How fun is this going to be here in a minute? It's not. But this is the kind of stuff that we used to have to do. Okay? And so that's far enough. Get a calculator, go to town. That's great. But that's the sort of thing we had to do back in the day, and you had to kind of see all these little tricks that, oh, I forgot about that. Yeah, they never go away. All right, here's the problem out of the book. That's where I was going. I forgot where I was headed. Here we go. 12.3, double integrals. Let's try this one.
What number is it?
This is number 16 in my book. So y squared e to the xy dA, where a, or where d, oh, so you're integrating it over d, where d is bounded by y equal x, y equal 4, and x equals 0. Okay? Now this is one where I probably don't need Desmos to graph what my region looks like. Here's y equals 1, 2, 3, 4. Here's y equals x. And here's x equals 0. So it's this region in here, yes? Okay? So I probably don't need Desmos for that business. Okay? So then the question then is this. In my mind, again, I want to see what that picture looks like. Okay? I probably want to see what that graph looks like kind of over this region. In my mind, I don't want to just get an answer and go, well, I think maybe. So I'm probably going to bring up my 3D calc plotter. Wherever you went, here it comes. Yeah, I was really disappointed with the 3D graphics on this thing. I thought it'd be cooler than it was. Y squared times exp of x times y, is that right?
Yeah, you did the next one.
Oh yeah, because it doesn't like exp. Oh, shut up, I got it. Leave me alone. E to the... Oh, because I didn't get a y squared in there anymore. That's the problem. Okay, there it is. Ooh, nice. Weird, huh? Strange. Now, if you're not sure which way to go with that, I'm just going to make my x, I'm just going to go in the first quadrant. I'm going to go out, we're going 0 to like 1, 0 to 2-ish, right? So I'll go 0, 2 maybe on the x. 0, 2. And 0, 2 on the other direction maybe. Nice. And let's go 0, 2 on the z while we're at it, I guess. All right. Which way is up, dummy? Oh, this is all the way up. Yeah. So that it goes up, you see? So it's headed upwards. So we're trying to find this volume down into this mess under here. Okay? But the idea, the point that I want to make here is it's all positive, right? I see y squared, I think positive. I think e to the anything, I think positive. So I think positive. How much positive? Well, not a ton. Not a ton. Okay? Not in that tiny little region. It's not a ton. Okay? So I kind of keep that picture in my mind as I go to do the work on this guy. Wrong picture. There's my picture. Nice. So again, if I type it in here, how do I integrate this thing? So what are my regions going to be? Am I going to do I want to do dx dy or dy dx? Kevin, no right or wrong answer. Which way are you going to go?
dy dx.
By God, all right. So dy dx, he says. And what will your bounds for y be? What's it bounded by below? What's this bottom function down here? X. Okay, it's x. And the top function is? 4. And then our x's are bounded by where? Our x's are bounded on the left-hand side by 0. And on the right-hand side by? By what? No. Can't have any y's in it. No y's. So, what's the biggest that x can be? It's where these two guys intersect, yes?
Oh, 4.
At 4. Okay? That's right. All right. So, you type that baby into your calculator. So, you know, integral y squared times e to the parentheses x times y, don't forget that, comma, y, comma, x, comma, or 0, yeah, x, comma, 4, x, comma, 0, comma, 4. That should do the job. What do you get?
Which ones?
So he said he wanted to do dy dx. So
Yeah.
y is bounded on the bottom by x,
Okay, that's
and the biggest it gets is 4.
4. And then the other one is just 0.
0
4,
over
then
to
x.
the biggest that x can be, and that's the number 4.
Gotcha.
You can't go to y because you don't want to bound it by a function, you want to bound it by a constant. What do we get? Your number?
Thinking.
Yeah, mine was 2.
Not bad, huh? Huh. Oh, me darn. Well, I could unrestrict mine, I guess.
Got a big number.
Uh-oh. I don't know that you're wrong. I just didn't seem like that big, but maybe.
Well, I think with the cube you were looking at it, I only got a volume of 1.
4.4 e to the 6. Yeah, I got 4 million. 4.4 million. Yeah.
Hold on. Well, it's not that I don't believe you. It just seemed like it seemed kind of big. Seemed kind of big. We'll see. But since you all got it, I guess maybe I'm not going to disagree with you. Yep, 4.4 million. Okay, well that's weird. Why was my thinking so wrong?
Because the cube we did was 2 by 2 by 2.
Oh, I need to go out to 4.
4 by 4 by 4.
Oh my God. Oh my word. Why didn't? Oh boy. That's bad.
What happened?
When I graphed it in the 0 to 2 by 0 to 2 by 0 to 2 cube, that was really dumb because my x's and y's could go out to a maximum of 4. And if I had gone out to 4 times 4 is 16. And so e to the 16 is fairly large. Times 16 is fairly large. And so, yeah, okay, I can buy that now. Whew. Like, geez, my little UB rectangle, it didn't look very big. Okay, well, do it right. Yeah. That wasn't so horrible. Now, Ian, you're backwards from us. You think I'm going to do it differently. This also could have been done really easily by how? You could have done it as
dx dy.
dx dy, and what would that have been? X is bounded by who?
X is bounded by y.
X is bounded by what on this side?
Oh, 0.
0. And bounded on the right-hand side by? Say it, y. And y is bounded below by? What's the smallest that y can be? 0. And what's the biggest that y can be? 4. Bam. Okay? The biggest place that this was brought home to, yeah, I remember doing this back in the day. Hey, we integrated, isn't that nice? Yay, we did that. But it was when I was doing my stats, when I was getting my master's degree, it's mostly in stats. We were doing these probability problems. We were talking about when you leave for, or when you leave for work is dependent on when you get up, okay, or something like that, or about, or the time it takes you to it takes you to drive to work depending on when you leave for work. So you could leave anytime between this time and this time. Well, then you're left with a certain amount of extra time between then and time work starts, yes? And so it has to do a lot with a situation like this, right? It's not like you can just leave anywhere between 7:30 and 8, right? If you can be like, I want to say, let me think about this differently. So you get up between 7 and 7:30, let's say, right? Okay, that's great. And it takes you a certain amount of time to get ready and stuff. So let's say you leave. And then you're going to leave on some other window over here. They're not independent of each other, right? This first decision affects the second decision, yes? That's what's going on here. We're not saying that y can be anywhere from 0 to 4. And we're not saying that x can be anywhere from 0 to 4. We're saying y can go from 0 to 4. That's true, but x is dependent on what that value is. So if you choose a particular y, we're out into this region, out into here, okay? And so we have to be, above that region to pull that off. Okay, that's where that came into play the most for me when I was doing this. I'm like, oh, that makes more sense now because, I know that when I leave for work is dependent on, or my time travel is dependent on when I leave, right? Because how much traffic or not. And so there's a certain time window. So if I decide to leave between here and here, well then I have a different time probability for this business over here. It's dependent on that, and that's where this big actually came home to me at. If you're doing it over a rectangle, probabilistically speaking, it's like the idea of you can get anything on the dice, you get anything on a coin flip or whatever, completely independent of each other, right? This can do whatever it wants, this can do whatever it wants, and you get the whole region of possibilities here. But if you get up totally late, you're not going to get to work on time, let's say. Okay, sorry. But I'm going to get easy traveling, Jay. You left too late, you ding dong. It doesn't matter how fast you travel, even in your F-18, right? No way you're going to get there on time. Okay, so it is completely dependent situation. There's parts of it that are just off. They're off the books now. It's not possible. There's no way that to happen. And so I think that was the thing that when I was actually doing stats and probability stuff with calculus, I'm like, that makes a lot more sense now because certain parts of these are off limits in this regard. It's not like I'm just making up. Well, this is a made up random problem, but it's not like we just make up random problems just to piss you off. See if we can fool you or something. This problem is. These actually have some ideas of what they would be. The only difference really is this function, y squared e to the xy, for this to be a probability density function, you would have to integrate the 1 over its whole region, which it doesn't. We could fix that. But if it did, then we would be literally finding a probability at that point. Okay. This isn't a probability, obviously, it's 4.4 million, so it's kind of hard to have that. Okay? But that's the game you play when you go into probability and stuff. It's the same basic procedure, just kind of come at it from a different point of view. Okay? But that's why we might be integrating from here up. Okay? Because it has to do with what x was. X was when you left for work or when you got up or whatever. Okay? So that's the idea of those. Y greater than x shows up a lot. Okay? All right. Well, tell you what, take a break for a minute. I'll come up with another problem. We'll do another 1 or 2, and then we'll jump into 12.4 and see where we end up. Good times. Good times will be had. There we go. Open. Oh, thank you. Good Lord, I almost forgot. I did forgot. Thank you.